translation, and the second one is rotation. Translation is when an object moves along a straight or curved line. On the other hand, rotation is when an object turns about an axis. Rotation has a variables, and it's divided into two. First is rigid body, and the other one is the fixed axis. Rigid body means that a body that rotates as one unit. All the particles are locked together. Fixed axis means that the rotation occurs but axis that doesn't move.
So in rotation variables, there is this figure, and the explanation is these two subsections. First, the pure rotation, angular motion. That is, every point of the body moves in a circle with the center being the axis of the rotation and move through the same angle during a particular time interval. That is the pure rotation. And for the pure translation, it is every point moves in a straight line and moves through the same linear distance during a particular time interval.
Now, as you can see in the figure 1 and figure 2, and figure 2 and figure 3, there's this line right here and there. What is this? This is the reference line. Reference line is a line that is fixed in the body and perpendicular to the rotation and rotating with the body. Now, the angular position of this line is the angle of the line relative to a fixed duration, which can be taken as the zero angular position, where the position is denoted by the theta. Now, the angle is usually defined and measured in radians, not in revolutions and degree. What is a radians? Radians is a notation of two lengths. It's a pure number and doesn't have any dimensions. It can derive from 1 revolutions, means 360 degree, equals to 2 pr over r, equals to 2 p rad, or after calculations, it equals to 57.3 degree. To find the angular positions of something, we can see the equations as is seen in the blackboard here. It can be seen that theta equals to s over r. S is the length of the circular arc, and r is the radius of the circle. As is seen in the figure 3, you can see that the radius of it is the s. Well, the theta that is apa tadi cari tuh?
2, 3.
Now, to find the angular positions of something, you can see the equations in front of you. Theta equals to s over r. S is the length of the circular arc, while r is the radius of the circle. As you see in the figure 10.3, you can see that the r is the s, while the theta that we are searching for is theta as is seen in the picture.
So, the next one is rotation with constant angular acceleration. So, in the linear equation, the v equals v0 plus a times t. In the angular equation is omega equals omega 0 plus alpha times t. The second one is when x minus x0 equals v0 times t plus half times a times t to the power of 2. In the angular equation is theta minus theta 0 equals omega 0 times t plus half times alpha times t to the power of 2. The third one is when v to the power of 2 equals v0 to the power of 2 plus 2a times x minus x0. In angular equation is omega to the power of 2 equals omega 0 to the power of 2 plus 2 alpha times theta minus theta 0. The fourth one is when x minus x0 equals half times v0 plus v times t. In the angular equation is theta minus theta 0 equals half times omega 0 times omega times t. The last one is when x minus x0 equals v times t minus half times a times t to the power of 2. In the angular equation is theta minus theta 0 equals omega t minus half times alpha times t to the power of 2. In pure rotation, the case of constant angular acceleration is important, and a parallel set of equation holds for this case. The next one is rotation with constant angular acceleration. The first one is when the linear equation is v equals v0 plus a times t, the angular equation is omega equals omega 0 plus alpha times t. The second one is when x minus x0 equals v0 times t plus half times a times t to the power of 2 equals to theta minus theta 0 equals omega 0 times t plus half times alpha times t to the power of 2. The third one is when v to the power of 2 equals v0 to the power of 2 plus 2a times x minus x0 equals to
So, in 10.5, relating the linear and angular variables, there are three conditions in rigid body. The first one is one revolution. It has one revolutions. The second one, it has same amount of time. And the third one is it has some angular speed or omega. So, the first one is the position. The angle here must be measured in radians. If a reference line on a rigid body rotates through an angle, a point within the body at the position R from the rotation axis moves a distance as along a circular arc. And the second one is the speed. Obtained by differentiating the position equations, we can write it as ds over dt equals to d theta over dt times r, or we can write it as v equals to omega times r. The angular speed omega must be expressed in radian measure. The linear velocity is always tangent to the circular path of the point. If the angular speed omega of the rigid body is constant, then the linear speed of v of any point within it is also constant, which is t equals to 2 pi over omega. The time for one revolution period is the angular distance 2 pi radian traveled in one revolution divided by the angular speed or rate at which the angle is traveled. The next one is the acceleration. The acceleration equation can be obtained by differentiating the speed equation or double differentiating the position equation, which is dv over dt equals to d omega over dt times r. The part of the linear acceleration is tangent to the path of the point in question. This can be called as the tangential component at of the linear acceleration of this point. Can be written as at equals to ar in radian measures. A particle moving in a circular path has a radial component of linear acceleration, which is ar equals to v cubes over r. That is responsible for changes in the directions of the linear velocity v. The linear accelerations of a point on a rotating rigid body has two components. The first one is the radially inward component ar, present whenever the angular velocity of the body is not zero, and the second one, the tangential component at, present whenever the angular acceleration is not zero.
Now, I'm going to explain to you about the linear speed. Linear speed is the value obtained by differentiating the position equation. As you can see, here's the position equations. From these equations, you got the linear speed. Now, for example, you got a circular plane, right? Now, the linear speed is the speed of the rotation with the direction that is perpendicular to the radius of the circle. Now, if the angular speed of the rigid body is constant, then the linear speed at any point within it is also constant. Next is period. Period is the distance 2pr traveled in one revolution divided by the speed at which that distance is traveled. The formula for that is period t equals to 2v divided by w. The time for one revolution is the angular distance to the rod traveled in one revolution divided by the rate at which the angle is traversed. So, period means how much time that is needed for one revolution to happen. Now, to further explain it to you, here are some sample exercises regarding the speed and period. For example, if you got a circular plane with a radius of 7 and an angular speed of, I'd say, 10. How do you calculate the linear speed? Now, you just write down the formula that put in all the value in there. See? Easy enough. Now to find the period, for example, if you get another circle with the same value of radius and angular speed, all you need to do is just write down the formula and put it all in it. Although for the period, because the formula didn't use the radius of the circle, we can assume that this one is not used. So you got 2 times 22 plus 7 over 10. Here you got 44 per 70 equals to 22 per 35. That's it for the linear speed. Thank you for watching.
Next part is the acceleration. The acceleration equation can be obtained by differentiating the speed equation or double differentiating the position equation. The equation can be dv over dt equal dw over dt times r. Next, the part of the linear acceleration is tangent to the path of the point in question. This can be called as the tangential component, at, of the linear acceleration of the point can be written as at equal alpha r. It is radian measure. Next, where alpha is the angular acceleration and must be expressed in radian measure. A particle moving in a circular path has a radian component of a linear acceleration. The equation is AR equal v square over r. That is responsible for change in the direction of the linear velocity v. And AR equal v square over r equal w square times r. The linear acceleration of a point on a rotating rigid body has two components. First, the radially inward component AR, present whenever the angular velocity of the body is not zero. And the second, the tangential component AT, present whenever the angular acceleration is not zero.
So I'm going to explain about kinetic energy of rotation. First, we cannot apply the formula K equals to half times m times v because to a rotating object it only gives us the kinetic energy of the center mass. Now we see from the figure, in the figure A, A long rod is much easier to rotate about its central axis than about the B-figure axis through its center and perpendicular to its length. The reason for that is because the difference is that the mass is distributed closer to the rotation in the A rod than in the B rod. So it is easier in the A. And then the equation is K equals to sum of half times M times I times W times R times I. So in a rotating object, to calculate the kinetic energy of the object, all of the particle kinetic energy must be calculated individually and then added up. Then for the rotational inertia, in which the mass of the rotating body is distributed about its axis of rotation, there are two equations, which is I equals to sum of M times I times R times I, that is the radian inertia, and then K equals to half times I times W, that is the radian measure. That is all for the kinetic energy of rotation.
Now, I'm going to explain to you about the torque. First, if you ever wondered why doorknobs are located as far away to the hinge as possible, here the explanation. So if you get a doorknob, right? With the doorknob, there's a force acting on it with direction like that. Now the force can be divided into two. The one that is perpendicular to the radius, and the one that is straight along the radius. This one is called Ft, well this one is called Fr. Ft stands for force tangential and Fr stands for force radial. Now if you see from here, from the center, the force radial is straight with the radius. This means that this force does not contribute to the rotations of the doorknob. The only one contributing is the Ft, or should I say tangential, which is perpendicular to the center, to the radius of the circle. Now from this phenomenon, we can get that torque equals to radius times force sin the angle at which the force happened. This means that the torque is a product of magnitude of tangential component Ft and how far from the center the force is applied. The torque itself uses the Newton meter unit. For example, if you get a doorknob again, let's see, doorknob with the radius of, I say, 7. See here, with the force acting on it, I'd say 10 Newton, 7 meters. With this, to make it easier, 90 degree. Now, to calculate the torque of it, you just need to put in the equations first. F sin theta equals to 7 times 10 sin 90 degree equals to 7 times 10. What should I say? 70 Newton meter. Easy enough, right? That's it for torque. Thank you for watching.
If we want to relate the net torque net on a rigid body to the angular acceleration that torque causes about the rotation axis, we can do so by using Newton's second law, which is F net equals to M A. M times A. M for mass and A for the acceleration. The torque due to the tangential component of the force causes an angular acceleration around the rotation axis. A simple rigid body free to rotate about an axis through O consists of a particle of mass m fastened to the end of a rod of length r and negligible mass. An applied force F causes the body to rotate net equals to I times A. We can prove equation this by using figure of 10.17. From figure 10.17, we can find the rotational inertia, which are torque equals to I times A in radian measures, and then torque net equals to I times A also in radian measure. And this equation can be extended to any rigid body rotating about a fixed axis. This is because such body can always be assumed to be an assembly of single particles.